So what I'd said is that we should be able to finish today, God being our helper, and then I'll give you 2 weeks to read for the second cut. I hope 2 weeks is enough. We'd already done a cut, the first cut, which had covered the non-steroid or not non-steroid, sorry, the narcotic analgesics. So we do need a second cut, because you do understand that for this, for you, your exams are end of year examinations. So we do need to do 2 cuts that cover everything we have studied. So the second cut should start from anti-Parkinsonian drugs. We did muscle relaxants, we did general anesthetics, we have done CNS stimulants, and of course, finally, we have done hallucinogens. So I hope 2 weeks will be enough, so that we can do our second cut. The other issue is I really pray and hope that we will change our culture of cheating, because even when sometimes I look at your cuts, I look at your assignments, there is obvious cheating. You know, some of you, I don't know how you hide your Mokenyas, but do remember, life will play you one day depending on the way you live it. So you cheat today, you think you are better than your lecturer because you can cheat and get away with it. You will not always get away with it. I mean, they say a thief has 40 days. So kindly just read. And sometimes you try to check what your friend has done, what your colleague has done, and they are also wrong. So you block your mind. You don't want to think. So I would urge you, just read well. The questions will be from what we have read, just as the questions will be for the final exam. So as I have said, it is my prayer that we should finish today. There is just the hallucinogens. I will not go beyond that. And in that, and most of the hallucinogens do not have any therapeutic indication, because they are hallucinogens. The side effects are very severe, hallucinogenic effects, as we had said last time. So most of them do not have therapeutic indication, but it is important for us to know some of these compounds. You know, we might not look at all of them, but know some of them, because they are actually being also abused by our people, especially these days. There's a lot of drug abuse, and especially because of the, I don't know whether you call them the socialites or the celebrities. Most of them, and even some of us for performance and what have you, are abusing drugs. So it is important for us also to understand some of these drugs, although indeed, as I have said, they really do not have any therapeutic indication because of the potent hallucinogenic effect or psychedelic effect that they have. So we had already mentioned the classical, the first class, which you call the classical hallucinogens, are the 5-HT2A receptor agonists. We had mentioned the main neurotransmitters, that these classical neurotransmitters have an influence on the serotonin, the dopamine, and then noradrenaline. The same as we have mentioned for the other conditions. Even when we talk about Parkinsonian, we said it's dopamine. When we talk about CNS stimulation, it is dopamine and even noradrenaline. So we had also mentioned the receptor agonists, the classical hallucinogens that we had already mentioned. We had mentioned the common features. I remember we went through them with you, and now we are at the phenylalanine. That is what we were discussing. And we are saying we do have some which are naturally occurring, like mescaline. It's a phenylethylamine. It's a phenylethylamine because on the alpha carbon, it has a hydrogen. It does not have an alkyl group. When it has an alkyl group, we go to the next class, which is the phenyl isopropyl amine, where we have amphetamine. And when we were mentioned, because we have discussed amphetamine as a stimulant, we mentioned the role of that small alkyl group. That's when it's a small alkyl group, like a methyl group, it blocks metabolism through monoamine oxidases, which metabolize these compounds through oxidative deamination to give the aldehyde. They could go to the alcohol, or they could go to the carboxylic acid, and all those byproducts are actually inactive. And we did mention that whenever we do substitution on the phenyl ring, when you do substitution of the phenyl ring, especially with methoxy groups, then the disortant compounds change from being stimulants to hallucinogenic. And we had given examples of 2,5-dimethoxy, and at position 4 you have a methyl amphetamine. So this is just the basic structure of methylamphetamine, but at position number 2 and 5 of the ring, it has a methoxy group. Then you also have 2, 5, and at position 4 is where these compounds are differing. You can have a bromo, you can have an iodo, and the larger the molecular weight it was found, the higher the hallucinogenic activity. And that is the naturally occurring mescaline, and you can see it is actually a phenyl alkylamine. It's even a primary amine, phenyl alkylamine, which has methoxy group at position 3, methoxy group at position 4, and methoxy group at position 5. It's a weak psychoactive compound, but it does have some some psychedelic activity, hallucinogenic activity, and it is found, it's naturally occurring, found in peyote cactus. We had already mentioned that. We had also looked at these compounds, and we are saying, depending on the structure, is it an isopropyl? Is it an alkylamine? And you can see the first one, when R is equal to a hydrogen, we have the phenyl ethylamines, and all we have done is substitution at the aromatic ring, and that substitution at the aromatic ring, it changes the activity, as we've already said, from CNS stimulant activity to hallucinogenic activity. And as you can see, we have a very good example already, we have said, of mescaline, but we have said also you can have other groups. And we have, of course, also the isopropyl, and you can see the difference there. When we talk about the isopropyl, the only difference is that you have this group. You have this group there. That is the only difference, that it has the small alkyl group, or more often than, or more correctly, a methyl group, because again, when you put a big group, you introduce steric hindrance, and when you introduce steric hindrance, the steric hindrance, you prevent that molecule from approaching, from sitting on the receptor, and therefore the molecule, although with good lipid solubility, will not be able to bind the receptor, and therefore will not have activity. So let us understand, yes, you can put big groups. The big groups, one, can change the receptor they are going, the receptor affinity, the affinity, or the type of receptor that the compound can join. Remember, we said when you put bigger groups, you move from CNS stimulant activity to anorexient activity. Now we are saying if you put groups on the aromatic ring, again, you move from stimulant activity to hallucinogenic activity, and therefore the molecule is able to bind the different receptors depending on the structure. So this methyl group, as we have already mentioned, very, very important, because it is retarding metabolism and therefore increasing the duration, or even increasing the concentration of our compound, allowing it to attain concentrations in the brain that can be able to get to the receptor, excite the receptor, and bring us hallucinogenic activity. This is just what we have talked about. The bigger the group, at that position, the more lipid soluble the group at that position, the more lipid soluble the group at that position. As you can see, the higher the lipid solubility of the resultant compound, and the higher the activity. It looks like the substituent on the phenyl group does not have much introduction of steric hydrants. Its main activity is introduction of lipid solubility of the resultant molecule. Then again, even when we look at now, these are just the different positions. This is position 2, 4, 5, and this position 1, 3, 4, 5. That's the only difference. And again, the larger the group at that position, the higher its lipid solubility, the higher the activity of that compound. So it's important for us to differentiate the roles of the different substituents. The substituents on the phenyl ring are more important in as far as lipid solubility is concerned, under selectivity for hallucinogenic receptor, whereas the groups on the acyl chain can retard metabolism, give the compound activity, but they can also introduce steric hydrants. They can also bring about selectivity or change of the receptor affinity, where we are changing from stimulant to anorexient activity. That is something we have mentioned before. Then metabolism, we have mentioned mescaline is a naturally occurring compound, so that's our mescaline there. It can be metabolized by the cytochrome P450 enzyme, and if that happens, cytochrome P450 enzyme, this group there can undergo oxidative O demethylation because it's an oxygen, oxidative O demethylation, and it will give us this methyl mescaline. And also that group there, and I think we had mentioned that before, can be also acetylated to give us the acetyl metabolite. Remember, when we acetylate compounds, we do not really give them higher water solubility, but we terminate, we bring a stop, we terminate their pharmacological activity. And more often than not, they then undergo glucuronide conjugation and they are removed from the body. This same compound can undergo metabolism by monoamine oxidases, and if that happens, then it will go through an aldehyde and it can give us the acetic acid derivative. That is through monoamine oxidase. And this monoamine oxidase, remember, they're the same enzyme that metabolize the neurotransmitters. So I think that is quite easy to understand. I don't think there's anything hard difficult there. Then we are still on the phenylpropylamine and amphetamine derivatives. Those are the phenylpropylamines. And we are saying again, just as we said with the stimulants, that if you put an alpha methylation of the phenylalkylamine, it increases CNS activity. I've already stressed on that because of retardation of oxidative deamination. It is not because it increases lipid solubility, it's because it retards oxidative deamination of the primary amine, and therefore giving that compound higher concentrations, which can get into the brain and bring us the activity. This activity may not be strictly through binding efficiency, but decreased metabolism due to steric decreased metabolism due to steric hydrons, as we've already mentioned. Alpha substitution produces optical isomers. Again, now here, kindly note that there is a reversal of the active isomer. When we looked at the when we looked at the stimulants, it was the S dextroisomer which was having higher activity. But now there is a reversal. When now we look at the hallucinogenic compounds, you find that it is the R levoisomer as opposed to the S dextroisomer when we looked at stimulatory activity. So again, that's very important because it's further emphasizing the role, the importance, the significance of stereochemistry in pharmacological activity. Then we can also note ortho meta or para substitution. Substitute amphetamine has no hallucinogenic activity. So if you substitute only one, you only substitute the ortho meta para. Mono substitution was found not to have activity. You do require either to have the disubstitution of the or trisubstitution for the amphetamine to actually have hallucinogenic activity. So we can note therefore the 2,5-dimethoxy or 2,5,4,5 trimethoxyamphetamine have higher hallucinogenic activity. So we are also saying therefore di and triaromatic substitution with methoxy groups increases psychotomimetic potency, as we've already said. The 2,5-dimethoxy, also 4-methylamphetamine, is a psychedelic and a substituted amphetamine. So when you put 2,5-dimethoxy and we add a methyl group or a bromo group or iodo group at position number 4, the resultant compounds have very high hallucinogenic activity. N-methylation, that is mono, decreases or abolishes activity or hallucinogenic activity. Again, this we can compare with the stimulant. When we look at methamphetamine, which is methylamphetamine, we did mention mono N-methylation with small alkyl groups, specifically methyl group, increase activity. Increases stimulatory activity, increase lipid solubility, increase stimulatory activity. But here, for the hallucinogenic activity, we are saying that the amine, which has the maximum activity or maximum potency, is the primary amine. So kindly be able to compare and contrast how the phenylalkylamine structure can be changed for stimulant activity and for hallucinogenic activity, because the basic structure is the same, but the structural modification can either give you a hallucinogen, can give you an anorexiant, or can give you a hallucinogenic agent. And I hope you are actually able to appreciate the differences in these compounds, or the differences in the SAR for either of the activities we have mentioned. This now is a basic structure. So we are saying this group here, we want it to remain a primary amine. We want to remain primary amine. Again, also try to also, we are going to look at the indole derivatives. As we move to the indole derivatives, also try to compare the SAR of the indole derivatives with that of the phenylalkylamine hallucinogens and even the phenylalkylamine stimulants. We did not have any indole stimulants. So quite kindly try to compare. And we are saying when it is methyl, you require 3 to 10 milligrams. When it is bromine, that DOB, you require 1 to 3 milligrams. And you can see when it is iodine, you require 1.5 to 3 milligrams. So we are therefore saying that depending on the group that you put there, then the compounds can actually have a very, very, very high activity. They can actually have a very, very high activity depending on the group. And the lower the group is in the periodic table, the higher the atomic mass, the higher the activity that that compound is showing as a hallucinogenic agent. Also, it was found, you see, this is now our dimethoxy. This stands for dimethoxy. It's a 2, 3, 4, 5, it's a 2,5 dimethoxy bromine. So it is a dimethoxy bromine. It has a 2-methoxy paradat or bromo. We can call it dimethoxy bromo. Of course, amphetamine. So you find that it has the two methoxy groups and a bromo group there. And then we are saying that it was also found that you can actually also, this compound DOB can be structurally modified to give us the more rigid phenylalkylamine, the more rigid. And if you look at this other compound, which was already not given a name, you find that the only difference is that this group here, this methoxy group there, the oxygen, the methyl, that is the oxygen, this is the same oxygen, this is the methyl here, this is the same methyl, addition of another methyl group, and then joined to the aromatic ring. That is the only thing that has been done. So the methoxy group has been changed into a furan ring, a dihydrofuran ring, and incorporated. That is, the methoxy group has been incorporated into the phenyl ring as a dihydrofuran ring. And the activity was even found to be even higher. So the rigid phenylalkylamines, when I look back, when we were looking at, no, it was not this class. It was another class where I remember it's another class, not this one, where we were looking at that sometimes when you have rigid compounds, at least a planar compound, it of course it has quite high lipid solubility for it to penetrate the membranes, and sometimes the lipid planar molecules are also able to bind the receptor quite well. So you can see rigid the phenylalkylamines, when you make them rigid, they have also very, very good activity. And that is not all. This methoxy group also can also be incorporated in now to the dihydrofuran, the benzo dihydrofuran ring. And again, still, you can see with increase. These are 22, this was 61, that was 1.2 micro. This is nano. So, of course, the nano is more potent. It shows you require much lower, you require much lower concentration to give you the ED50 and that means higher potency. And again, if you compare this compound with this compound, all that has been done, again, base methoxy group, the oxygen is that oxygen, that methyl group is that methyl group there, and then addition of a methylidine A group, and because here you can see there is a double bond there. In this one, this one there was no double bond, but now for the next compound, indeed you make it a benzofuran. You can see this is a benzofuran, and that is also a furan. So you can see that slight change, increasing the rigidity of this compound. Put a double bond there, put a double bond there, and all we want to understand, say, is that also it was found that the phenylalanines, they could be changed, they could be modified or manipulated to give as rigid compounds, and even the rigid phenylalanines were also found to have much high psychedelic or hallucinogenic activity. The fully aromatic compounds is the first alkylamine derivative to show higher potency than LSD. So we are therefore saying structural modification to develop rigid phenylalkylamines still resulted in very high activity. And that is all we study about the phenylalkylamines. And then quickly we move to the tryptamines. And remember, tryptamines are the indoalkylamines. The indo is not new to us. We did mention, we discussed at length the indo, non-steroid anti-inflammatories. We give drugs like Todorac, we give drugs like indomethacin. So the indo ring is not new to us. And here, when we talk about the indo ring, if you look at the structure of serotonin, which I had given you before, you find that serotonin is, of course, a neurotransmitter. You look at serotonin, you can't be able to see that serotonin has an indo ring. And therefore, when we talk about the indo derivatives, we are talking about compounds that resemble serotonin. When we talk about the phenylalkylamine derivatives, we are talking about compounds that resemble both dopamine and noradrenaline. So the indo derivatives, which were found to be hallucinogenic in nature, are structurally resemble serotonin. So the endoacyl amines, but we will start just the way we started with the phenylalanine. We say the phenylalanine molecule does not have any activity. It has high polarity, rapidly metabolized, and therefore cannot have any neuroactivity. And the same case applies to serotonin, has no psychoactivity or oral administration due to rapid metabolism. That we do expect to be the position, and high polarity. You know, serotonin has a hydroxyl group at position number 5. We call it 5-hydroxytryptamine, and therefore it has very high water solubility. It is rapidly metabolized in the body, and therefore it will not have any neuroactivity. Structural modification, and first we look at the N substitution, and we can start that N monomethylation of tryptamine gives a compound with no activity. So remember, so here methylation has no influence on activity. NN dimethyl gives compounds again with no oral activity. So when you look at the indo derivatives, when we methylate, we do not improve on activity. Again, the receptors are different between these compounds and the other compounds we have mentioned. NN dialkylation with appropriately large groups give active compounds. So again, remember when we did mention alkylation earlier, we said if you put large groups, you will reduce activity. If you put small groups, like when you look at amphetamine, it has an N-methyl group, small group, monomethylation brought in increased activity for the phenylalanines, especially the phenylalanines, the stimulants. For the stimulants, when you looked at the stimulants, when you did monoalkylation, methylation, like amphetamine, you did increase activity. We have mentioned for the hallucinogens, we want the primary amine. So kindly remember that also. So in your mind, as we discuss the structure of these different compounds, you need to jog around these ideas in your mind, such that you can compare these three different classes. We have the stimulants, which are phenylalkylamines, we have the hallucinogens, which are phenylalanines. We have the hallucinogens also, which are endoacyl derivatives. So we are saying for the endoacyl derivatives, we require to put slightly larger groups. So here, the steric hindrance is not an issue. The issue is for these compounds to identify the receptor. The 5-hydroxytryptamine or 5-HT is 5-hydroxytryptamine, and the methylation of 5-hydroxytryptamine gives a compound bufotenine, which is a very weak, very weak hallucinogen. Very weak hallucinogen, but again, mainly because of the hydroxyl group and the fact that the groups that we have put on the nitrogen are very small. We require either slightly bigger groups, and we require also the hydroxyl group to make it less water soluble, to give it lesser water solubility, so that this compound can be able to penetrate the BBB. Methylation, when we methylate the hydroxyl group of bufotenine to give 5-methoxy-N dimethyltryptamine, it increases activity. Why? Because we are saying when we methylate the hydroxyl group, then we are blocking or we are decreasing the lipid solubility of that compound, and the compound has higher lipid solubility. It is able to penetrate the BBB and be able to get into the brain and therefore bring hallucinogenic activity. Remember, the structure is such that it has a methoxy group. It has a methoxy group, and therefore it is increasing that activity. So that's our tryptamine there. That is our serotonin. That is our bufotenine. And we have just said bufotenine has that hydroxyl group, just like serotonin, but it has the small methyl groups. And we did mention that the small methyl groups cannot give us significant activity, but you would require something else because of the hydroxyl group. Now, when we block the hydroxyl group, we are getting now this compound, which we are calling the 5-methoxy-N dimethyltryptamine, and this compound has been found to be highly hallucinogenic. This compound, the 5-methoxy-N dimethyltryptamine, has been found to be hallucinogenic. So it's a potent, rapid-acting psychedelic compound and entheogen. Remember, we did mention all these names from the tryptamine family, often derived from the bufo alvarius toad. So it's found. It is produced from the bufo alvarius secretions, toad secretions, and you can, again, there are some toads which are very poisonous. Again, these are things that you will do, or you have done, or if you haven't done them, you should mention them as you discuss, as you study pharmacognosy. That is the area of the pharmacognosists. So I hope you will do realize and we do appreciate that plants and animals, all of them, they can be poisonous. Even snakes produce venom. So they can be, even animals can produce, not only plants can be toxic or can produce toxic byproducts or phytochemicals, even animals can. Then from there, we are looking now at the dimethyltryptamine, which we did mention. When you look at dimethyltryptamine, it really does not have, dimethyltryptamine does not really have any psychedelic activity, because the minute you give it, and we did mention, it is rapidly metabolized in the gut. It undergoes fast-pass metabolism in the gut through oxidative deamination, and therefore no activity. But as you're going to study again in pharmacognosy, there are some teas, hallucinogenic teas, especially I think produced in South America. Some of those hallucinogenic teas, what they do, they get different plants with different compounds, with different phytochemicals. One of the plants inhibits the metabolism of one of the byproducts in the other plant. And therefore, when you take that tea, combined, not one plant, combined plants, you find that one of the compounds is an inhibitor of the metabolism, like of DMT, and therefore you can have, when you combine those compounds, you make a tea, and that tea can indeed be hallucinogenic. So we are talking about DMT containing tea. A traditional South American psychoactive decoction is brewed from that plant. These are things that you're going to you are studying. You're going to study in pharmacognosy. And what does it contain? It's containing monoamine oxidase inhibitors. And plants like that, what do they contain? They contain DMT. So if you have DMT and you combine it with another plant which has monoamine oxidase inhibitors, what will happen? The monoamine oxidase inhibitors from one plant will inhibit the monoamine oxidase inhibitors which within the body, which are metabolizing the DMT. So the DMT will be bioavailable to bring about pharmacological activity. Again, very important for you as you discuss plants and their toxicity, that you can have a plant which is not toxic, but when you combine those plants, they can have toxicity because of synergism or because of blocking or because of metabolic interactions, and one plant blocking the metabolism of another plant. So you can see that, and this tea is definitely can be abused. It is used in spiritual, we had mentioned, shamanic, traditional medicine context to induce profound, long-lasting psychedelic experiences. In the absence of the monoamine oxidase inhibitor containing plant, the tea has no psychedelic effects, and we can ask why. And the answer we have already given. The DMT is a psychoactive ingredient, but it is not orally bioavailable because it is rapidly, as we have said, undergoes fast-pass metabolism through oxidative through oxidative N-deamination and to give the acetic acid derivative. But so it's rapidly degraded by monoamine oxidase enzymes to give the indole-3 acetic acid. You can be able to draw that. The inhibitor blocks the oxidative deamination of DMT, and the DMT is already available. So such a simple combination of plants can change one plant from being safe. It has the toxic compound, but it is still safe. And it is safe because the compound, the body is able to get rid of that compound very, very rapidly. But once you do the mixing, once you do the combination of those various plants, some with monoamine oxidase, some of them do have harmine. So with the monoamine oxidase inhibitor and the DMT, there you will have a concoction which indeed can bring about a lot of can cause a lot of hallucinations. So that was the first. So that therefore that was the dimethyltryptamine, and now we are still looking at the derivatives of the tryptamines, and we'll go to another one which is also naturally occurring, which is found in mushrooms. So you have heard of very poisonous mushrooms. Again, you will, even if you haven't, you're going to study them in pharmacognosy. That is why we work side by side. We do have some mushrooms that contain psilocybin, and this is a tryptamine hallucinogen. They contain psilocybin, which is a tryptamine hallucinogen. I hope you can be able to see the difference between these compounds and serotonin. So if you look at this compound, psilocybin, it has a phosphate at position number 4 as compared to serotonin, which has a hydroxyl group at position number 5. But when this compound is taken and it gets into the body, it can be hydrolyzed. At that point to give us psilocin. So psilocin is the hydrolyzed psilocybin, or psilocybin, we can call it psilocin phosphate, because psilocybin is psilocin phosphate. So once it is hydrolyzed by phosphatases, then it gives us psilocin. Now, when you look at your psilocin, we can ask ourselves, what is the difference between psilocin and serotonin? What is the difference between psilocin and serotonin? Or even bufotenine. What's the difference between bufotenine and psilocin? Because you can see this is similar to bufotenine because it has the dimethylamino group at that position. The only difference is that the hydroxyl group position has been changed. In psilocin, the hydroxyl group is at position number 4. In bufotenine, the hydroxyl group is at position number 5. And therefore, we can actually call those the compounds constitutional constitutional positional isomers. Constitutional positional isomers, they have the same functional group, the hydroxyl group, but it is in different positions. So that's why we're calling them constitutional positional isomers. And that change of the position of the hydroxyl group from position 5 to position 4 makes the resultant compound be psychedelic or have hallucinogenic activity, and we are going to explain that in a minute. I hope you have appreciated the difference between psilocybin and psilocin. The difference is that psilocybin has a phosphate at position number 4, whereas psilocin has a hydroxyl group through the metabolism of psilocybin. So now we can look at all this. So serotonin can be converted. If you look at that, can be converted to psilocybin. And if that happens, the group there has moved to position number 4 and has changed to a phosphate. There is a dimethylation of the terminal nitrogen. Of course, it's at physiological pH. We know it's a dimethylamino group. It can be protonated. It is protonable at physiological pH, and that is why you see that positive there. We have already mentioned bifotenine. Bifotenine, the difference between bifotenine and psilocybin is the fact that that hydroxyl group is at position number 5, and that is a phosphate which can be converted into hydroxyl group, but at position. Then this is just how tryptophan is made in the body from tryptophan, which is an amino acid decarboxylation to give us, of course, tryptamine, and then that can be structurally modified, especially in the plants that we are saying will produce the psilocybin. They can structurally modify that compound to give us now the hallucinogens. So this starts with L-tryptophan. It is tryptophan because it has the carboxylic group, and then we have aromatic amino acid carboxylase. That is an enzyme we have mentioned when we were talking about the Parkinsonism, carbidopa, and so on. We did mention aromatic amino acid decarboxylase. So that enzyme can also bring about the decarboxylation of L-tryptophan to give us tryptamine. And then the tryptamine, we can have tryptamine methyl transferase, tryptamine methyl transferase. And when you have tryptamine methyl transferase, it will bring one methyl group there and also bring a second one so that you will get the methyltryptamine. So this will be a two-step process, and you have dimethylation of the primary amine, and now we have the dimethyltryptamine, and then you can have 4-hydroxylation. They're looking at the synthesis of psilocybin, 4-hydroxylation, and once the hydroxyl enzymes. Once you have that, and specific at position number 4, you will get the psilocin at your position number 4, and then now you can get psilocin kinase, the psilocin kinase, and now the psilocin kinase will bring about the phosphate group. It uses a kinase, it requires ATP for it to be able to do that work, and it will change psilocin into psilocybin. And this compound in plants is usually found, or in the mushrooms, it will be in the psilocybin state. But now when you take the mushroom, and this has happened to quite a number of children where their parents have gone to the forest, there is famine or there is lack of food, and we find these wonderful bright mushrooms which are not even eaten by the animals. And you don't ask yourself a question, you just think that luck is on your way and God has provided a meal. Unfortunately, once you take those mushrooms with the psilocybin, they will be converted into the psilocin, and the psilocin, as I have said, is highly, highly hallucinogenic, and indeed it can even cause death. It will be fatal to those who will consume those compounds. Psilocybin versus bifotenine. These two compounds are constitutional isomers. As you've already mentioned, you can see the structure is the same, only the change. There is critical difference in their pharmacological activity. Psilocin is orally active, whereas B49 is not. And that is what makes these mushrooms very, very poisonous, because once you take them converted into psilocin, and the psilocin has a lot of hallucinogenic activity, as we have already mentioned. And now we want to understand how come psilocin has activity and serotonin serotonin does not have any activity. Remember, we did say of course, serotonin has an amino group at a primary amine. Of course, when you talk about psilocin, it is a dimethyl, it's methylated. That, of course, increases the lipid solubility slightly, but that is not enough to account for the high hallucinogenic activity of psilocin compared to serotonin. And the main reason, of course, the dimethyl group does help, but the main reason why the psilocin has much, much higher activity is because of the shift of the hydroxyl group from position number 5 to position number 4. When that hydroxyl group is shifted from position number 4 to position number 5, what happens is that it is brought closer. The hydroxyl group and the nitrogen are in close proximity. And because they're in close proximity, the hydroxyl group and the terminal and the nitrogen can form hydrogen bonds. So once they form hydrogen bonds, the hydrogen bond will utilize the lone pair of electrons on the nitrogen. There will be a decrease in the polarity of that compound, and you're going to see all the points. So one of the reasons is that the hydroxyl group and the terminal nitrogen are brought much closer to each other. And because they are brought much closer to each other, they are able to interact through a hydrogen bond. And once they interact through a hydrogen bond, we are therefore saying that the nitrogen has lower basicity, and it has lower basicity because its lone pair of electrons will be utilized by the deficient hydrogen to form hydrogen bonds. So each lone pair of electrons is now, it makes, since it has been utilized, makes that nitrogen less polar. It also, the lone pair of electrons is also less available, so that compound is protonated at physiologic pH, and therefore again resulting in less ionization. So, and therefore ultimately that compound, when you have the hydrogen bond where the nitrogen has lower basicity, also there is this we are calling shielding. It has been shielded. When you bring in the hydrogen bond, you're bringing in a shielding of the nitrogen. It has been shielded even from metabolism by the monoamine oxidases. So those three reasons: one, you've decreased ionization, you have decreased the polarity, you've shielded the terminal nitrogen from rapid metabolism. It will undergo metabolism, but not at a very high rate as will happen for the other drugs, like the other compound, like serotonin, like B49, and so on. Because of the shielding, there will be lesser rate of metabolism. Because of their shielding, the lone pair of electrons will be less available for protonation, and therefore lesser degree of ionization. Again, we have also said, because of the shielding, the compound, we have the compound will be, we have said, lesser protonation, it will have lesser metabolism, and of course we have talked about the lesser ionization. So all those three things are the ones that actually bring about the activity of psilocybin, even now even when you eat it in the mushrooms. When you eat it in the mushroom, because there is that hydroxyl group being changed from position 5 to position number 4, and of course there is also demethylation of the terminal nitrogen. Now that molecule has much lower water solubility. It has slightly higher lipid solubility. It has also lesser tendency of undergoing ionization. It has also lesser tendency of being metabolized. And all those three factors put together allow that molecule to penetrate the BBB, get into the brain, get attached to the hallucinogenic receptors, and bring about the psychedelic activity. So psilocin you're saying the reasons for its activity compared to B49, compared to the other compounds. The hydroxyl group, or even the serotonin, the hydroxyl group of psilocin is a little bit closer to the amine, the terminal amine. It is able to form a hydrogen bond between the 4-hydroxyl group and the 3-ethylamine groups. This hydrogen bond shields the electron non-pair amino group from deamination, as we have said, by monoamine oxidases, which means that unlike B49, psilocin is orally active. You have reduced the rate of metabolism. The hydrogen bond also decreases the molecule's proton accepting capacity. In other words, it decreases the basicity. It pushes it more. It decreases its pKa and therefore increases its Ka, and the compound becomes more basic. So basicity, low pKa, decreases its rate of ionization. It decreases, it has slightly higher Ka, it has slightly lower basicity, and therefore a lower rate of ionization. At the blood pH, there is more psilocin in the non-ionized lipid soluble already mentioned. all the dehydrogenases, which you give the oxidation product, which is the carboxylic acid derivative. All we wanted mainly to understand is that that compound indeed is, unlike serotonin, unlike B49, it is a very strong, very, very strong hallucinogenic agent because of the shift of the hydroxyl group from position number 5 to position number 4, giving very close proximity between the terminal amino group and the 4-hydroxyl group to allow them to interact through a hydrogen bond. And once that interaction happens, then the resultant compound, its polarity goes down. And once its polarity goes down, it has higher lipid solubility. Also, its rate of ionization goes down. Its rate of metabolism goes down, and therefore it can't reach concentrations which are high enough to bring about a hallucinogenic activity. This is still the same, just showing the various changes that can be done at that position of the indole derivatives. You can see for the indole, unlike, remember, when we were talking about the phenylalanine, we said when you just put one substitution, you get almost no activity. But for the indole, just one substitution is enough. Remember, for the phenylalanine, we said you either have the 2,5-dimethoxy, or the 3,4,5-dimethoxy, or the 3 and the 4, you can put a different group, and the 5, you can have a methoxy. So again, remember, these very, very prominent, they are very obvious differences between these different compounds for them actually to give us the same activity. So when this is a hydrogen and that is a hydrogen, you have 5-methoxytryptamine. And that's a hydrogen and that's a hydrogen. We get 5-methoxytryptamine. That is actually the difference between that and serotonin, is the fact that here it is a methoxy group and in serotonin, and in that compound, of course, that is a methoxy group, and it has almost no. The one which we did mention has activities where when you have 5-methoxydimethyltryptamine, that one we did mention, it has some activity. Then if you have you have a hydrogen and methyl, again, you find that was said not to be known. It's activity not to be known, but as we have said, when you have 2-methyl and you have when you have a methyl and a methyl, we already had mentioned, and that gives psychedelic activity. When you have a methyl and isopropyl, it's a mixed complex activity. And then the other one, in fact, that's what I've done for the next group. I've removed the ones which are not very important. So what we are saying here is that tryptamines are extremely sensitive to substitution on the indole ring, and nearly any substitution besides those shown previously results in diminished activity. So what can give us activity is when you have a methoxy group at position number 5, and a dimethyl group at position at the nitrogen. So if you change, there are not many acceptable substitutions, and you can see the substitutions we have here. So very few substitutions are responsible for psychedelic or responsible for hallucinogenic activity. Switching the indole ring for another heterocycle, such as the benzofuran, remember I mentioned the benzofuran or the benzodiazepine, produces compounds with modest but diminished activity. So somehow the indole ring, do you understand why is it ideal? Because this indole ring is the ring that is found in serotonin. So when you change that ring, furan, I mean it's an oxygen. Here you put an oxygen or you put a sulfur. There was activity, but it was lesser than the activity given by the indole ring. And we can't be able to explain that because when talking semblance with the indole ring with serotonin, and therefore those compounds that have the indole ring will compete with serotonin for the same receptors. So these are the ones which were, these are the most important here. These two, those ones were found to be positive psychedelic, and we had already made the dimethyl diisopropyl. That was also very, very active. And also we did mention the 5-methoxydimethyl was also found to be a very potent psychedelic activity. I think this we have already mentioned. We don't need to go back there. So what is the SAR? We mentioned usually the SAR of all these compounds. And again, now we are looking at the indole derivatives. We have looked at the SAR of the phenylalanine as both stimulants and also as hallucinogens. So now we are looking at the SAR of the indoacylamines as hallucinogens. And then dimethyltryptamine is inactive orally, effects clear very rapidly, because with orally, remember we said it's not active orally, but if you give it with monoamine oxidase inhibitors, then even this, you give it the monoamine oxidase inhibitors, it can have activity. Remember, we did mention that. And then dimethyl, the same as with this is dimethyltryptamine. The other one was dimethyl. The other one was dimethyltryptamine. It's the one we had discussed. DMT combined with hermine. Hermine is a selective monoamine oxidase A inhibitor, will bring about activity. That's where we were discussing the teas, which have got hallucinogenic, which are used in religious festivities, and of course used as hallucinogens. Alpha methyltryptamine slows monoamine oxidase activity and increases lipophilicity. The same thing we had mentioned as the same thing we had mentioned even alpha methyltryptamine, the same thing we had mentioned when we were talking about the others. Anytime you put an alpha methyl group, again, it slows down. Alpha methyl is at that position. It will slow down metabolism in the tryptamines. It also increases the lipid solubility, and the compounds will have much higher activity. So that was for the stereochemistry. And we are saying alpha methylation introduces chirality and optical activity. Again, see the difference. We have reverted back. We have the R-ribo isomer has higher activity than the S-dextro isomer. The same thing that we had mentioned before. For hallucinogenic activity, it retains, whether it's the phenylacylamines or it is the indoacylamines or the indoamines, the stereochemistry remains the same. The R-ribo isomer is the one which has higher activity than the S-dextro. Remember that S-dextro was for the stimulant activity for the phenylacylamine, like amphetamine. We talk about dextroamphetamine. It is the one which has the higher activity. So again, when you look at these compounds, and that's an amino group, you put an methyl group there. We've already said a methyl group at that position increases activity, it blocks, it retards, it brings about metabolic retardation, and therefore the compound can be metabolized slowly, and therefore it will attain high concentrations in the blood, and those high concentrations will help this compound to reach higher concentrations in the brain. And that is the main one we did mention about the stereochemistry. I think we have also mentioned the other SARs, and then of course of importance is the stereochemistry, and we have mentioned the other SAR just as I mentioned for the others. So in your mind, it will be important when you read to be able to compare those different classes of drugs or compounds, very similar and yet also very different. We mentioned the phenylacylamines as stimulants, and then we also mentioned the phenylacylamines as hallucinogens, and then we have mentioned the indoacylamines as also hallucinogens. It is important for us to understand how structural modification can change a compound from one activity to another activity. So we are done with the first. We are done. We have looked at estimate 5HT. We have looked at the tryptamine, and we have stress psilocybin, which is converted to psilocin, and we have looked at the phenylethylamines, and the phenylethylamines we have mentioned should not have been phenylethylamines, should have been phenylacylamines should be the better one. Phenylacylamines, because we also discussed the isopropyl derivatives, which should be phenylacylamines, and also the phenethylamines in that group. So now we are on the last one, which is the egolines. And under egolines, we have the lysergic acid diethylamide. Lysergic acid diethylamide. We are done now with the tryptamines, and we have given examples. And the main one there is psilocybin and psilocybin. And of course, the compound that we have said can cause a lot of havoc, even in families, where if you eat the wrong mushroom, of course, there are some mushrooms that are food mushrooms, or they can be used as food, but the others that are very poisonous. And we have already mentioned that. So it's important for us to note. And as I said earlier, animals, God's wisdom, they have God's wisdom. He is the one who created them. And you will find, if you find an animal does not eat a certain plant, just eat that plant alone. Because somehow the animals don't die. Even in the forest, they will select the edible plants and leave the other plants. Of course, I do believe that these plants which are poisonous, or even animals which are poisonous, they must be producing a certain chemical which can be can be sensed by the animals, and therefore allowing these animals not to eat those plants. Any change? So now you're looking at LSD, or lysergic acid diethylamide, and you can see we are calling it lysergic acid diethyl. This is the reason why we call it diethyl. This group there, diethyl, that group there is an ethyl. That's an ethyl, that is an ethyl, and that ethyl, and then the whole compound, if you look at it, it's an amide. So we call it lysergic acid diethyl amide. And now we are saying any change in the amide substitution results in substantial decreased importance. So we are saying this amide, very, very important. Inactivity. Again, when we look at this compound, we should be able to see that indeed it has two chiral centers. It has that chiral center there at position 8, and it has a chiral center at position number 5. Again, changing the chirality at position number 5 and 8 can change the isomer that you have, and I believe we are going to look at that in a minute. LSD, extreme in vitro potency, does not correlate well with its 5-HTA binding, indicating additional mechanisms may be responsible for its unusual potency. It's a highly potent hallucinogenic agent, and it's not the mechanism of action that it acts as a 5-HT2A agonist is not enough to be able to account for its activity. That's all that point is saying. That, and I think we had mentioned also that more often than not, these compounds can have mixed mechanism of actions. How do you preparation and stereochemistry? LSD is prepared by reacting a lysergic acid with diethylamide. Lysergic acid has a chemical composition, that one. It has 4 different isomers because it has 2 chiral centers. It has 2 chiral centers at position number 5 and at position number 8. And since the number of isomer is 2 to the power n, where n is the number of chiral centers, then we can be able to understand why it has indeed 4 isomers. It has 4 different isomers. Only the 5R, 8R dextroisomers are psychoactive. Again, relevance and significance of stereochemistry. And we have mentioned all along, even when we looked at all of them, the stimulants, the hallucinogens, we are talking about stereochemistry. Even when we mentioned many drugs, we talked about stereochemistry playing a major role or major significance in drug activity. And of course, the stereochemistry, why it does play a major role is because it will give you different types of isomers which might have different sizes, that will have differences in their electronic charge, will have differences in their sizes, and there are differences in their steric hydrants. And the molecule that has the proper size, the proper shape, will be the molecule that will, or the necessary shape and size, is a molecule that will interact with the receptor to give us the optimal activity. So for LSD, we are saying 5R and 8R, and that also is a dextroisomer. A racemic mixture of LSD shows only half the potence of the dextroisomer, because when you mix them, as we have said, it's one isomer that has the maximum activity. So for sure, if you mix them, you will have a reduction in the activity. This is our LSD, and as we have said, it has 4 isomers. And you can see that is our LSD. And when this has the beta orientation, and this has the beta orientation also, because you see they are RR, position 5, position 8, when they all have the beta orientation, that is our SLSD, and that is the most active. That is a dextro R isomer. But when you put LSD in basic media, there can be equilibrium between LSD and iso-LSD. And when you look at iso-LSD is when you retain the beta orientation at position number 5 and position number 8. You have the alpha orientation. That gives you the iso-LSD as the other isomer. You know, when you have two, you can have the various. Then you also have the LSD. The LSD now is when this retains the beta orientation, and the position 5 has the alpha orientation. Again, the L is different from iso, just it's the opposite of the iso. The LLSD, again, in basic media, can again undergo epimerization, because this is a kind of epimerization. And when it undergoes epimerization, then both the positions will have the alpha orientation, and that is the L-iso LSD. You can have the L-iso LSD. Kindly note which isomer changes to which. LSD changes to the iso LSD. LSD changes again to the L-iso LSD. And all of those are just names depending on the orientation of the substituents at both position 5 and 8. It's also important to note that they form an equilibrium. So the LSD can change. So iso-LSD and the iso-LSD can change back. So there is that equilibration of those products, or those epiisomers. And we are done with that group, which was the egoline, and the egoline derivative. The best example of the egoline derivative is LSD. That is the best example. And again, when you look at it, kindly note it's an alkaloid. It is an alkaloid. It's an egoline derivative. It is an alkaloid, and responsible for binding the receptors, the 5-HT2A receptors, and bring about hallucinogenic activity. So we move now from that class to number 1. So the second class was serotonin releasing agents. Serotonin releasing agents, and the serotonin releasing agents are mainly derivatives of amphetamine and methamphetamine. Those are the ones which were found to be serotonin releasing. Again, remember, they will release because there is structural resemblance between serotonin and these compounds, and they can be taken up by the transporters and get into the vesicles, replace serotonin, and therefore release the serotonin. And some of the examples is 3,4-methylene dioxymethamphetamine. And you can look, if you look at this, up to there, that is methamphetamine. So you can have either 3,4-methylene dioxymethamphetamine or 3,4-methylene dioxyamphetamine. And the MDMA, the 3,4-methylene, 3,4 position 1, position 2, position 3, position 4. So if you look at position 3 and position 4, they have, this is the methylene there, deoxy. So you can see where the name comes from. That group there is a methylene deoxy. So methylene deoxy, then methylamphetamine, because the compound is methylamphetamine. Okay, so, and that is what in the market out there is called ecstasy. Could be some of you have heard it, but I hope none of you has taken it. So methylene deoxide, methamphetamine stimulates serotonin release through membrane transport system responsible for the reuptake and storage, as I've already said. And therefore, there requires to be structural similarity and also structural difference, so that this compound has structural similarity with serotonin, but it has also structural difference that allows it to bind those transporters more firmly, and therefore once it more of a lot of it is transported into the serotonin vesicles, it will displace the serotonin and it is released. It causes derealization, depersonalization, and other alterations of consciousness. Remember, we did mention, of course, the balance of all these neurotransmitters is very important. The minute you are off balance, you will have issues. And like classical hallucinogens, the methylene deoxide, 3,4-methylene deoxide, methamphetamine has some significant toxicity issues, and of overdoses can result to death, because they can give you what we call serotonin syndrome. They are releasing a lot of serotonin in the body. They can give you serotonin syndrome, which can be fatal. Remember, we did mention that most of the drugs that bind the serotonin receptor, or the 5-HT 2A receptors, they generally do not have a lot of toxicity. Of course, there are some which can have toxicity, because always there are exceptions, but most of them do not have a lot of direct toxicity. It is the side effects that they bring, all the change in the personality, the perception of issues, that all of a sudden you are a human being, and all of a sudden you feel, you think you can fly. All of a sudden, your ability to perceive a sound, to hear a sound is changed over. And now the sound is, the stimuli is changed to something that you can see, visual stimuli. So, as I had explained last time, it becomes so difficult because you could see a snake and you are seeing beautiful colors, and you want to pick the colors. So what happens? You're bitten by the snake. You see a train coming, and all you can see is beautiful colors. The sound, the brain interpretation of the stimuli is completely distorted. And when that is distorted, instead of you hearing the sound, you are seeing colors. And that is what these drugs do to people. And once you see the colors, you will go for the train. You want those beautiful colors, and all of a sudden you'll be crushed. You can fly. I mean, of course you cannot fly. And you climb the highest tree or the highest building, and you challenge your friends, and you are telling them you can fly. And because all of you, birds of the same feather flock together. So all of you are thinking the same. So none of those who are already on those drugs can give you the right information. In fact, they'll tell you, yeah, I know you are competing. Climb up, you fly, and I'll be after you. And you can see I'll do it better than you, because all of you under the influence of the same, and none can correct the other. And so that kind of overdosage results in serotonin syndrome, where you have increased heart rate, increased blood pressure, increased body temperature, and that can result in shock and death. So those are serotonin-releasing agents, and it was found that the methylene dioxyamphetamine has much higher activity than the methylene deoxy, methamphetamine. You'd expect the methamphetamine, the ecstasy, to have much, much more activity but the reverse was found. And this is because of something we have discussed before, depotization. The methylene methylamphetamine has too high lipid solubility, and therefore there is depotization, there is redistribution. Once it gets to the receptor, very high lipid solubility, and because of the high lipid solubility, it leaves the receptor and moves out. The same also, it's a larger molecule and it does not sit well on the psychedelics receptor. So those two properties make the methylene deoxyamphetamine to have much, much higher activity than the methylene deoxymethylamphetamine. So again, you can, the interpretation of lipid solubility, the interpretation of steric hindrance is not always the same. There are those where you do substitution and the molecule is better bound on the receptor. Like we talked about, the methylamphetamine has higher stimulant activity. Now we are saying the methylene methylamphetamine has lower activity than the methylene deoxyamphetamine. Although the methylene deoxymethylamphetamine has higher lipid solubility, because of that reduces its activity. It will penetrate the brain much faster. But unfortunately, when it gets into the receptor, there will be redistribution, and that will result in its lower activity. So kindly, I find most of the students, they always will quote this lipophilicity, high activity. But if you talk about lipophilicity, high activity, like if you remember when we discussed, of course, there will be higher potency, like for even the barbiturates acting as general anesthetics, as we discussed. But we talked about the duration of activity to be much shorter because of depotization. So even as you discuss some of these factors that will influence the activity or the biological activity of molecules, let it not be a song. There is some relationship between the influence even on stereochemistry and the group of compounds. We have looked at the stereochemistry. We have seen that the stereochemistry of the different classes of drugs results in different isomers having the higher activity. So even as we discuss some of these factors, let us also remember that the factors can influence different molecules differently. But there is a general influence, but there can also be specific influences for specific molecules. Synthesis, again, simple method of synthesis, basic scheme is the oxidation of the plant oil called saffron, which has also this big name there, 1-3,4-methylene dioxybenzene. You can see it's methylene dioxybenzene. So that is saffron. So basic scheme, oxidation into a ketone. You can see that one, saffron oxidized into a ketone, which is then condensed with methylamine and reduced the final methylene deoxymethylamphetamine. You can be able to draw the structure of methylamine. So you're saying this. So you first of all reduce that to the 3,4-methylene deoxy, 3,4-methylene deoxyphenyl 2-propanone, and you can see that compound. And then after that, you go to step 2, reversible imine formation. So now you are starting from that compound there, and it is reversible. The first one was not reversible, forming the ketone. The second one, where the ketone is being converted into an imine starting with an I. Whenever you have carbon double bonded to a nitrogen, we call it an imine. So again, we had this kind of structure, a lot of it, when we were looking at the cephalosporins, when we were looking at the oxines and so on, we did mention this group. So again, it's not really new to methoxyimine and so on. It's not very new to us. So when that ketone converted to the imine, reversible imine formation, this occurs spontaneously when the ketone is placed in a solution with methylamine. So that happens spontaneously, not in the hydrochloride salt. So it is the base methylamine that forms spontaneously, and that gives us the imine, and then the last step is reduction. Again, now that is the imine. Reduction can be removal of oxygen or addition of hydrogen. So you can see this addition of hydrogen, also a reduction of hydrides, aluminum mercury, amalgams, or electrical cells, or catalytic hydrogenation permanently converts the imine to the methylene deoxymethylamphetamine. Again, you can see the arrow there is a bold arrow. It is not, it's a single arrow. There is no equilibrium. The equilibrium is only in the conversion of the ketone, to the imine, not any other, not any of the other processes. So that is a simple way that we can make the ecstasy. Again, as I have said, ecstasy is a drug of abuse. It's a drug of abuse. It does not have any pharmacological or therapeutic indications, but it will be abused because of, as it causes euphoria. It also as it causes the hallucinogen. It's a hallucinogenic agent, but also it will cause a lot of euphoria, and therefore people don't care. I think there are people who live for today. If I get the excitement today, I do what I want. I want to make money as a musician. I want to go there on stage and impress on anybody. I live for today. What happens tomorrow is not an issue. But you see, the problem with these things is that you start with a small dose, you get very good effect, but with time, the body demands more. And you continue increasing the dose until you take the legal dose. And then also quite a number of people also have a tendency of also not using these compounds singly. They will take this one, they will take cocaine, mix with this one, mix with alcohol, and so on and so forth. So, as I have said, I think it is living a life with no purpose, because life is not just making money. Life has a lot of meaning, especially when you are healthy. Because the minute you start thinking these things, the problem is now you are no longer healthy. You have a mind challenge, and the mind diseases are just like any other diseases. And indeed, they can be worse. They're actually worse because, as we have discussed before, they change your personality. They change your perspective, the way you perceive things. So perception. So they change so many things. I mean, for you, abnormal, what is considered abnormal under normal circumstances, for you, it is normal. So you do crazy things. And at times, of course, when you wake up tomorrow morning, you are reminded, hey, what's happening to you. And because you become now again very ashamed, you're very embarrassed. Again, you go again and you want to take more so that you can accept yourself. But the more you take, the more, of course, you sink into the problem. So the metabolism of the methylene deoxymethylamphetamine. So we can either start with the oxidation, the N demethylation. Sorry, we can start with the N demethylation. You can see the N there has two methyl groups. So here we are starting the oxidative N demethylation, and when we get that, we are getting the mono. So that becomes, that you remove that methyl group, and you remove the methyl, remove that methyl group. So now you get methylene deoxyamphetamine. All of us are aware now what is the compound. So you get the methylene deoxyamphetamine, and then now that compound can go demethylation, and in demethylation, it's just removal of that methylene group there, and you now get the position 1, 2, 3, 4 dihydroxyl. So you get the 3, 4, it's position 1, 2, 3, 4 dihydroxyl again amphetamine. 3, 4 dihydroxyamphetamine, and then this can undergo now catechol O methylation, using the methyl transferase, and when that happens, one of that can be methylated. Usually the one which is closer can be methylation 1, 2, 3. The position 3 can be methylated, and now that time we get the 3-methoxy And at position number 4, sorry, we still have hydroxy. So it is hydroxymethoxyamphetamine. I hope you can just that. Hydroxymethoxyamphetamine. And that again, there is question mark. So that is our final product. Then we can start on this other side. And the only difference is that there is a switch on which metabolic process we start with. With this other one, we are starting with the demethylation, whereby you start with removing the methylene group. But the steps that happen are the same. So it's only that this one starts with the demethylation, catalyzed by cytochrome 2D6, the same. So even if you don't remember the enzyme, you're still saying cytochrome P450 enzyme, and therefore you lose the methylene to give us the 3,4 dihydroxy. This one is still methylamphetamine, and then the catechol or methyl transferase. And when that happens, it now gives us the methoxy derivative, and then this is questionable. Still not, perhaps it is not yet very certain, but it is thought that that compound can still undergo demethylation, can undergo oxidative and demethylation to give us the dihydroxymethylamphetamine. So that is the simple route of metabolism of those compound. You can see, incidentally, I hope you note that in this particular compound, in the metabolism, somehow, that's why we said some of these metabolic processes or even the chemistry of these compounds, it's compound specific. I hope you do note that the monoamine oxidases don't seem to play a part in the metabolism of mNDMA. The enzymes that are playing a major part is the oxidative N-demethylation, which are cytochrome P450 enzymes, and demethylation. Those are the main compound, the main enzymes that are playing a part. And that is because, remember, we didn't mention, because of this methyl group, this methyl group retards, especially the monoamine oxidases. It retards the monoamine oxidases, and we say that is the role of that alpha methyl group. It retards metabolic process through monoamine oxidases, and they have to bring about the formation of the acetic acid and the aldehyde. So you can see that what we have discussed in the chemistry, even when we come to look at the metabolism, is actually also followed in the metabolic process, whereby because of the methyl group, that methyl group deters, or that methyl group retards the metabolism of vitamin or amino group through oxidative deamination because of steric hydrons. So that agrees with whatever we have already looked at. Another compound which was also found to be a very potent serotonin-releasing agent is a 4-methyl diamphetamine. This is just a different group. Somehow it was also found to be very potent. The other ones you are looking at methylene deoxy, but it was also found that 4-methyl diamphetamine is also a highly selective serotonin-releasing agent. It additionally inhibits the enzyme that breaks down serotonin. So that drug is just a second drug from the MDAs and the methylene deoxymethylamphetamine. It's just another drug which was found to be a serotonin-releasing agent. Then we move on. We're almost at the end. We move on to the next category, and these are the NMDA, N-methyl D-aspartate, N-methyl D-aspartate, and this we did mention is a specific receptor, and we're looking at drugs that antagonize that receptor. And we're looking at drugs that antagonize that receptor, and drugs that antagonize that receptor. We did mention at specific drug concentrations like ketamine. It can bring about depressive activity, and it did be used as a general anesthetic because the NMDA receptor we did mention it is a stimulatory. Uh, it is a stimulatory receptor. So when we antagonize it, we can get general anesthetics. At the same time, there are some of the compounds that bind for ketamine. It can bind that receptor and bring about hallucinogenic activity, and the compounds that bind this receptor to bring about hallucinogenic activity, we also call them dissociatives. The N-methyl D-aspartate NMDA receptor, which we are calling NMDA-R for the receptor, is a predominant molecular device for controlling synaptic plasticity and memory function. And we do have some of the compounds that can bring about a bind antagonist activity at that receptor. We have phenylcyclidine, which is PCP. We have dextromethorphan, which we have discussed, and we have said it's an antitussive, and of course we discussed it as a morphinan. And then we have ketamine, which we have discussed as a general anesthetic. We have not discussed this, but the methoxetamine is very similar to ketamine. It has similar structure. Difference being there, you have methyl group, there you have ethyl group, and in this one, at the ortho position for ketamine, you have a chloro group, and this one, at the meta position, you have a methoxy group. So you can be able to say that they ketamine and methoxetamine are actually similar as structural analog. They are structural analog with very simple or very little structural modification. When we look at the NMDA receptor, which we had mentioned before, we did mention glutamate or aspartate can bind, is the one which binds this receptor, and once it does so, it can bring about a calcium channel. It is a calcium gated channel. It can bring about calcium release. And of course, we did mention that glycine is also necessary as a coagonist. So the glutamate, the aspartate are some of the NMDA itself, and that's why it's called the NMDA. When it was discovered, they had used this compound, N-methyl D-aspartate, and it was found to stimulate that compound, the first time they discovered those receptors, and that's why they call them NMDA receptors. But they can also be stimulated by glutamate. As we have said, we do require the coagonist glycine to bring about the optimal activation. Activation of NMDA receptors requires binding of glutamate or aspartate. Aspartate does not stimulate the receptors as strongly as the glutamate. In addition, NMDA receptors also require the binding of the coagonist glycine for the efficient opening of the ion channel, which is part of this receptor. So, and this is nothing new. We had mentioned that we do require the glycine and also either glutamate or the aspartate or NMDA itself. When we look at ketamine, we've already mentioned ketamine, and we did mention we do have the isomer. We have 4 times more active than the S-ketamine is more active than the R-ketamine in this activity. And we had mentioned it when it undergoes metabolism, we form the no-ketamine, which we had said is about twice as active as ketamine. This again is not news. We had already discussed ketamine when we're discussing the general anesthetics. PCP, which again is a drug of They are standardized and you are taking them as drugs because of a pathological condition that you have. Perhaps you have a depletion of a certain agonist like a dopamine in Parkinsonism. But now when you take them when you do not have any pathological condition, you are taking them in non-standardized doses for sure. That is how you will get these complications, because it is important for us to understand that we have these receptors in the body, and they are used through endogenous agonists to help in the normal functioning of our bodies, to maintain the homeostasis. This is something, again, we discussed when we were looking at the prostaglandins, that you require the homeostasis, you require a balance of this when we were talking about, when we were discussing inflammation. You require homeostasis. You require a balance of all these compounds in the body. Once any of them is out of balance, either through consumption of these drugs of abuse or illegal substances, or even consumption of too much of the drug, then you will get the toxic effect. So that is important for us to understand. So the cannabinoids are a type of chemical in marijuana. The main active cannabinoid we have mentioned. Cannabinoids activate their cannabinoid receptor 1 and receptor 2. The CBA1 is a G protein coupled receptor responsible for the psychoactive effect of the cannabis. But in the bodies, they have their own role. And these compounds are usually not hallucinogenic, but cause relaxation, euphoria, and munchies. So that is what most of these compounds, the cannabinoids, that is what they mainly cause. And you see the euphoria, the relaxation, you feel relaxed, you have no worries in the world. So this is the cannabinol. Again, when you look at these cannabinols, you can see they have quite a complex structure. And you can, when you look at that compound, you look at the tetrahydrocannabinol, which is the active compound in cannabis sativa. You can see the difference between the cannabinol and the tetrahydrocannabinol. That difference is in this ring there. You can see that ring there. That ring is a benzene ring. But in the tetrahydrocannabinol, that ring is a dihydrohexene ring. It's a dihydrohexene ring. And therefore, that is what not dihydro, it is a hexene, actually. we would call it, we would number the position of the bond. We are to, depending. So it has double bond at that position and that position. So it's actually a hexene, whereas this is a benzene. So we have changed from benzene to a hexene or cyclo, to a cyclohexene ring, and that is what brings a difference. Otherwise, the whole other structure is the same. That's why we are calling it tetrahydrocannabinol, because if you look at it, there would be a double bond there. That position, there will be a double bond there. So you have put 4 hydrogens and no wonder the tetrahydro, so that it changes from the benzene to a cyclohexene ring. Change from benzene to a cyclohexene ring, and that compound, the tetrahydrocannabinol, is the one we are talking about, giving us the activity. How are they metabolized in the body? Again, most of these compounds through cytochrome P450 enzyme, that's our tetrahydrocannabinol, alicyclic hydroxylation. Again, we have mentioned alicyclic metabolism. That is when you have a double bond or you have a multiple bond. When you have a multiple bond and you have some further, the chain is long, then the carbon next to the multiple bond can undergo hydroxylation. That is what we call alicyclic hydroxylation. When the carbon next to the carbon carrying the multiple bond. We did mention this when we were mentioning the barbiturates, that some of them can undergo alicyclic hydroxylation because of the double bonds. So if you look at this compound, you can see this here, that carbon there. This carbon is the one next to the double bond, and therefore that carbon there can undergo oxidative hydroxylation, and that is alicyclic hydroxylation. So kindly note that is alicyclic hydroxylation, and depending on which of the carbon, because even this one here, so that even this one here, is also can also undergo alicyclic hydroxylation, depending on which one undergoes the hydroxylation. Of course, the methyl group would be very fast in undergoing hydroxylation. Then you will get your compound. So this is the 11 hydroxy THC. I hope I had numbered in the previous one. Yes, I've given you the numbers here, so you can look at the various positions. So this carbon there is position number 9. That position there is position number 8. So I've numbered so that you can be able to differentiate the positions. Then you can have hydroxidation. You can see this is a methyl alcohol. That is the hydroxyl group is not directly attached to the ring. So that methyl alcohol can undergo oxidation to the carboxylic acid, and that will give us the THC carboxylic acid, which is indeed an inactive metabolite. And of course, it has in fact slightly higher water solubility. Then also the THC can undergo also, again, catalyzed by cytochrome 3A4. The first one was catalyzed by cytochrome 2CA. So the different positions seem to have different alleles of the cytochrome P450 enzymes catalyzing the oxidation. So for the 8, this one we say this is still alicyclic, or allelic, not alicyclic, allelic, because this is a double bond. This is also another carbon which is next to the double bond. This carbon also next to the double bond. So allelic hydroxylation can either happen at position number 11 or it can happen at position number 8. This was position number 8, and it will give us the 8 hydroxy THC, or it can give us 11 hydroxy THC. So in most of that, and then again we can still have another. Now even after getting that one, we can still have another allelic hydroxylation at now that position, so that both positions have the hydroxyl group, and that gives us the 811 dihydroxyl THC. That again is mainly allelic, quite understandable. So when we look at the CBI receptor location, nerve cell membrane receptors primarily in the brain and in the spinal cord. So the CBI and the CB2 receptors are there in the body. What are the endogenous ligands? Arachidonic acid derivatives. So these are some of the ligands that bind those receptors, and they bind those receptors so that there can be, as we have mentioned, homeostasis or proper functioning. Because, you know, we subject the body to different stimuli. You subject it to exercises. It undergoes different stimuli, and therefore you do require the body to produce. When you are subjected to specific stimuli, it will produce the endogenous, either agonist or antagonist, so that homeostasis is maintained. Clinical importance mainly is for substance abuse, obesity. So that is the clinical importance for that compound. The CB1 receptor's major role in the brain is to regulate the release of neurotransmitters such as serotonin, dopamine, and glutamate, again homeostasis. So that is the main importance of those receptors, the CBI receptors you have in the brain. But now when you come and activate them erroneously by using illegal substances, then of course you will get those other things that you have mentioned. And some of the compounds that have been found to bind, or some of the endogenous compounds that have been found to bind that compound, if I see, we said arachidonic acid derivatives, we have the arachidonyl ethanolamine, also known as vilothamine. Vilothamine, it is an endo for endogenous, endocannabinoid antagonist at CB1, but an agonist at CB2. Another endogenous compound, the 2-arachidonyl glycerol 2AG, it's an endocannabinoid agonist. I will just give you those. We mentioned that the compounds that bind the CB1 and CB2, we have endogenous compounds, and they will be formed when the body needs them, and they will be formed in the amounts that are required, just like any of the other compounds. But you see now, when you take other compounds, which are exogenous compounds, as we have mentioned, they will excite, and one of them is the cannabis sativa. They will excite, they will have the THC, which will excite these receptors, and once these receptors are excited, then you will have high levels of all these compounds. You have high levels of those compounds. You can see serotonin, you can see dopamine there, you can see glutamate, which is an excitatory neurotransmitter, you can see serotonin, and therefore once you have those high levels of the neurotransmitters, then you will get the conditions or the things that we have said. You will get excitation, you get euphoria, you will get relaxation, and all those things. So also, and so we are still moving, you're almost at the end. The other one, these are not very detailed. We have the K-opioid receptor, and the location is the cell membrane of nerve cells in the brain, and again the spinal cord, just like the previous one. And the endogenous ligands is the dynorphins. The endogenous ligands of the K-opioid receptors are the dynorphins, and our body, we produce enkephalins and we produce dynorphins, and that is why sometimes when you do exercise, you feel elated, you feel excited. Actually, for some people, when they do exercises, they even feel euphoric. And that's why some people get even addicted to exercises. This is because when you do the exercises, you produce the enkephalins, you produce the dynorphins, and they have their K-opioid receptors, and they will bring you the euphoric. They will act like you've taken a bit of morphine. You know, they will bring about the euphoric feeling, and that is why exercise for quite a number of people brings about a lot of relaxation. It also, in fact, kind of activates, you know, like when you're feeling dull, you're feeling very dull, you're feeling depressed. If you pick the last drops of your energy and you move into the field, play football, run, you actually leave a more excited person because of the production of the enkephalins and the dynorphins, which are able to bind this receptor. Targeted for, so clinical importance, targeted for analgesic effects, and potentially natural addiction control mechanism. So you can see they can bring about an analgesic effect within the body. Also, they can, as I have said, they can also bring a bit of excitation, and especially when you talk about exercises, and they are also potentially a natural addiction control mechanism. You can see these receptors that are in the body have a function, but now you go and take compounds that will excite those receptors irregularly. So now we have an example like norphylapine hydrochloride, which is an antipyretic, an antipruritic agent or anti-itch. It's a K-opioid receptor agonist. So of course, when you take it in high concentration, it can bring you problems. You have also ibogaine, again, a naturally occurring compound, anti-addiction and hallucinogen. So these are some of the compounds that we have as the K-opioid receptor agonists. Psychoactive ingredient, also in tabananth, iboga or just iboga, ibogaine. Ibogaine interacts again. I believe you do these compounds again. That's where all the units also interact, because there's a lot of pharmacognosy. You will study those because you should be able to study plants which have abuse potential, plants which have medicinal value, and so on. So you should be able to mention these plants or these compounds in pharmacognosy. Ibogaine interacts with the 5-HT2A, also NMDA. So you can see this one has multiple modes of action. It interacts with 5-HT2A, NMDA, we have mentioned, and also the K-opioid receptor. It has significant stimulant effects because once it interacts with the NMDA positively, it will bring stimulation. But once it interacts with the other receptors, also it will bring also hallucinogenic effect. Hallucinogenic dose appears to be several times higher than the stimulant dose. It is known for its extreme duration, with the most intense effect lasting for almost 24 hours. So, and this is a plant. That's why also we have to also be very careful about plants. Its after effects include difficulty in sleeping, which may last for an additional 2 days. So this again is a natural iboga, is a naturally occurring compound. Is a naturally the ibogaine is a compound from iboga. So ibogaine is a naturally occurring compound, and you can see it can either be taken for stimulation or it can be taken for its hallucinogenic effect. What changes the dosage taken? Again, as we have said, this ibogaine is a compound that has multiple modes of action, and we mentioned all of them, so nothing new there. Last one, I believe. I hope. Yes, that is the last one. It is again a naturally occurring compound. So from salvia, the richness, the diversity that is found in our plants. There's a lot of diversity. There are so many, and quite a number of you have studied projects. Actually, you look at from the ones who have started on their projects. Most of your titles are phytochemical analysis, antimicrobial activity, perhaps antifungal activity, and so on. And if you are able to go further to do perhaps your masters and your PhDs, you will now even isolate those compounds. You will identify them through an MR and so on. So we are seeing the diversity in the richness, or in what we can get from plants. We can get that which has a lot of therapeutic importance, and we know plants are a source of a lot of therapeutic agents. But at the same time, we are saying also plants can kill. Plants can be sources of compounds or phytochemicals that can be stimulants, that can be hallucinogenic, that can even have other activities, as you already know. So even as we look at plants, let us understand that the forests have a diversity of phytochemicals that can also have a lot of pharmacological activity. And we're looking at, we have just looked at the previous, we have just looked at the previous compound, which we called ibogaine. We have looked at also THC. All these are plant-based. So we are looking at this salvia A is a principal psychoactive component of salvia divinorum. It has a unique mechanism. It's a K-opioid receptor agonist. It is a non-alkaloid. You look at it, when you talk about alkaloids are compounds that we have a nitrogen within their rings. They have a nitrogen somewhere. But if you look at this compound, that is a furan, it doesn't have any nitrogen. So it is non-alkaloid, which is quite interesting, because most of the compounds that have been found to have any most of biological activity are actually alkaloids. It produces dissociative effects with uncontrollable laughter, sensations of motions. Remember, we did mention that creeping, feel merging with or becoming objects. So you have that feeling that there is a wall, but you are feeling that you are able to, you are passing through it. And when you pass through that wall, you merge with it, crazy things and overlapping realities. Other realities that, effects that are not normal, are not in existence. And therefore, as we close, because actually we are coming to a close, I hope you have understood how the plant, all products, a product can be used for good or can be used to damage. Because we have talked about ketamine, which is a good product when used for a particular age. We even specified the age, and even at a particular dose. And the same compound can be used, as we talked about, as a dissociative compound. Therefore, when we look at these compounds, we are looking at them today, not because they have any therapeutic indication. And you can also go and read about cocaine. I did not agree, which is also a CNS, a very potent CNS stimulant. We are looking at these compounds so that when we go out there, we also have an understanding. When we face our community, we have an understanding of the fact that there are some compounds that are in existence that are being abused, either by increasing their dosages, using the wrong route of administration. It is supposed to be taken orally. They are injecting it and so on. They are inhaling it and so on. They are smoking it and so on and so forth. And therefore, as we understand the drug molecule, as we understand this drug molecule, we understand it in wholeness, that it can be used for its goodness, or it can also be used for its negative effects. And as a conclusion, I want to recite this from David D. Nicholas. And David D. Nicholas states that hallucinogens have a unique and powerful ability to affect the human psyche. They may alter one's concept of reality, may change one's views of life and death. You are feeling you cannot die. You are immortal. And can provoke and challenge one's most cherished beliefs. Therein lay the root of much of the fear and the hysteria that these substances have been fostered, that these substances have fostered in our society. So even as we are trained as pharmacists, let us know that our life can change today. Our beliefs, our perception, our psyche can change today if we change in the way we use compounds, we use drugs. They can be drugs that are beneficial. But as I have said, you can change the route of administration. You can change the dose. Some of the drugs or compounds are well known only for their CNS stimulation, for their influence on the psyche. The decision is yours. You have a big role as you move out there into the community, not to condemn those who are already victims of this compound. But your role as a pharmacist is to try and rehabilitate them because you understand the power of these compounds. That the wrong decision which was made is that first decision which was made to take the first dose. Because after you take the first dose, you no longer have control. And the drug, the chemical gets into your body. And it is the one that controls you. It is the one that commands you. So your role as a pharmacist is not to use the same drugs to negatively influence your clients so that they can come for more and more these drugs so that you get rich. Your influence in the community is to understand those who are abusing these drugs, to have empathy, to have love for them, and to be able to change them, to be able to rehabilitate them, so that although might never be completely normal, they can live a quality life. And I think with that, we close that semester today, where the semester we have closed it today, and we have looked at quite a number of CNS drugs that act at the CNS, drugs that are of importance and drugs that are of abuse. What will be your role in the community at large? What will be your role to yourself? Will you know these drugs and decide, I want to feel excited, I want to feel euphoric? Remember, the minute you start taking these substances is the first step, I will tell you with honesty, to your destruction. Your career, your profession will be destroyed. Because one of the things you will do, even when you are employed anywhere, you will be looking. You will be altering the records. You will alter the records so that you can get just a dose of these drugs, because you will always crave for them. And the crave is not a crave that can be satisfied. The more you take, the more you need, the more you crave for them until they kill you. So it is my prayer that after we understand these drugs, we'll be more careful into ourselves. We will be more careful to ourselves and even to those we serve, so that we do not introduce people to drug addiction and drug misuse. And just like some children say, when I grew up, my father or my mother I only saw them laugh. Even one of the drugs you said causes a lot of laughter. I only saw my mother relaxed. I only saw my father being a friend. He could only share what he had when he drank alcohol. That is the only time. And therefore, to me, I thought alcohol is a good thing. It makes my dad better. It makes my mother better. And therefore, even us ourselves, even as parents, we can actually introduce, from very early ages, we can be the people who introduce or who make our children to be alcoholic. You have to be careful as a pharmacist that you do not. There are even pharmacists who are there at the chemist, and when somebody comes and just a bit of, I'm in a bad mood, pop, I'll prazola. So what do you do? I can't sleep. And immediately you give them a sleeping pill. I have this problem. Immediately you even give them a CNS stimulant. What you are doing, what you need to tell them is that this thing, or unless if it is excessive depression, you don't even give them the drugs, because you don't know what kind of a mental illness it is. You advise them, kindly see a psychiatrist, or kindly be cancelled, kindly call yourself for a meeting, kindly resolve with yourself, kindly sit with yourself and see what are the issues within yourself that are making you not sleep. Because even if you take the drug, They will only work for a short time, and then you get addicted, and from there you will require a stronger drug and for every other dosage. So as you practice as a pharmacist, it is my hope that you will always ask yourself, what am I doing? Even not only for these drugs, even for antibacterial agents. Am I the one who is peddling this? Am I the one who is giving other dosages? So when somebody tells me they have 50 bob, that 50 bob, I must convert it to some drugs. Am I the one who is also bringing about drug resistance? So as a pharmacist, as you go out there, make sure that before you serve any patient, you ask yourself that question. What role am I playing? Am I a healthcare provider or am I a healthcare destroyer? It is up to you, because by the time you finish 5th year and we release you and give you the oath, you or the drugs, anything. A pharmacist can, as long as you go with your badge, you can get anything because you can give any reason. So kindly use these drugs effectively for the patient care and not to destroy yourself or the patients. And I think with that, I close the chapter until we see each other again. Thank you very much for your time.
Excuse me?
Yes.
Can you comment on the use of hallucinogens on terminally ill cancer patients?
For terminally ill patients?
Yes.
All right. What we do for terminally ill patients is that we try to improve on their quality of life. We try to use the quality of their life, and therefore, if you have any compound at very low dosages that can improve on the quality of the life of that patient, then you give it at controlled dosages, because even terminally ill patients, we give them morphine, we give them all those compounds. So sometimes we talk about the risk benefit ratio. And if this patient, of course, we are not God, but nevertheless, God has given us the understanding and the knowledge to know that whatever we do, whether we give this patient these drugs or not, they are still going to die. And that is the same case when we look at pregnant mothers. Sometimes we say, whether we want it or not, if I do not give this mother this drug and risk the life of the fetus, the mother will die. So what option do I have? I am not God. Yes, I'm not God, but the knowledge I know is that the condition that this mother has will kill the fetus. So you pray and you say, let me save the mother, because if I save the mother at the expense of the fetus, she can live to get many more. But if I don't, both of them will die. So what I would say about use in a very controlled setting of whether they are hallucinogens or they're narcotic analgesic, use of these drugs, if it helps the quality of life for the short period that patient lives, then they are worth using. They are worth using, but they must be used in a controlled environment with highly qualified professionals who know what they are doing, such that you can have a person who can condemn you to death in that, and professionally. So they must be used under the care of highly trained and qualified professionals in a setting which is only for them. And that is why you get hospice, you get a hospice, or you get settings which are only for the cancer patients, which are visited by highly qualified and trained personnel who know where even drug monitoring is done, so that these drug levels are also highly controlled. I think that would be my comment. When you talk about terminally ill patients, what sometimes we look at is the quality of life. Quality of life that they can manage today more comfortably. The pain is extreme and they keep screaming. So you give them quality of life. Sometimes, as I have said, it is the risk benefit ratio. Either way, a patient will go. But do they go in pain or in no pain? And once they go, they will leave and they go in lesser pain. I think to me that is better for the patient, and not only for the patient, even for the relatives. It is more comfortable for the relatives. But as I have said, under specialized setups and also under professionally trained personnel. Have I answered your question?
Yes, you have. I've understood.
Thank you very much. So I wish you well. Actually, after this, this semester I will not be teaching. I'm proceeding on my leave. So I think if I'm going to teach any of you, I will meet next semester. Thank you very much for your time. I apologize for the delay, but our bodies are subject to other problems. As you are aware, I was unwell at some time, and therefore I was not able to cover the syllabus on time. But I'm very thankful for your time. Kindly read well so that when we do our cut in 2 weeks' time, I will offer myself, whether I'll be on leave or not, to come over to give the cut, because we do need to evaluate, proper evaluation of the whole unit, considering that it's an end of year exam. And you can choose what to do. You might choose you not do Dr. Kamau's question. I cannot ask you. You will choose what to do, and therefore proper evaluation when we have students doing end of year exam is important. So that's why I'm still insisting on a second cut. So with that, those many remarks, I wish you all the best this semester. Work hard, because at the end of the work, there will be a crown, but nothing good comes easy. Thank you very much.